Hi everyone, we'll start in a couple minutes. Can everyone hear me okay?
Yes.
Thank you. Was there any questions about anything we talked about on Wednesday? No questions about Wednesday. Okay, so if you guys remember, on Wednesday we were talking about chapter 1, just an introduction to impact evaluations. Okay, so we covered one reading and there's still one reading left, so we'll cover that today. And then we'll get into chapter 2, which is about causal inference and the counterfactual. Okay. I don't know why. Okay, just an update on assignment number 1. As you guys saw in the calendar, it will be due on what date? I think April 26th, which is a Sunday. I'll just make sure I'm correct. Yeah, so Sunday, April 26th. And I will post that by this Friday so you guys can start working on it. And to answer it, I will go over this Wednesday with you guys some code using Stata. So we will just cover super basic functions, and with that, you'll be able to answer the assignment, okay? So if you're having any concerns about using coding, definitely be here for Wednesday's class. And yeah, that's all I have to say. Again, everyone can hear me. If you have any questions, you can put it in the chat or use your speaker. And if you can't hear me or you want me to talk slower, just let me know as well. Great. So what else did I want to say? For the referee report, it's not due for a while, but if you guys could start choosing your papers, looking through them, and let me know which one looks best for you. About half of you guys have responded and chosen a paper, and the other half haven't. So just get back to me whenever you're ready. Okay, so we're gonna start now. I'm gonna share my screen. I also posted the papers for chapter 1 and chapter 2, so you guys can look through the actual papers if you want to supplement the notes. If you're not clear on any of my notes, go back to the paper and that will give you your answer. Okay. Entonces vamos. Sure. Okay, so where are we? Chapter 1. Okay, so right now we're going to cover a paper called Retrospective versus Prospective Analysis of School Inputs, the Case of Flip Charts in Kenya. Can anyone remind me the difference between a retrospective study and a prospective study? Who remembers? Anyone? Don't be shy. We talked about it on Wednesday. No one? Okay.
I had a question in the paper of Esther Duflo. Why they had two control groups? I mean, why the theory of that?
Right. I guess they wanted to look at the effect of having a, where's the chat, sorry. So basically, when you have two different control groups, you want to see a different type of effect. So one of the control groups, I believe, didn't receive the iron salt at all. And so it's as if a treatment effect from going from no salt to going to some salt, or to having the salt for free. And then the other control group, I can't exactly remember what it was, if you can remind me, but I think it was that they had the option to pay for the salt. So then it's looking at willingness to pay. If people aren't just giving it for free, will they still pay for it? So I think that's why they had two different groups. They wanted to know whether it's only important if they give it for free, or whether people will pay for it. And that's an important policy question, because when we're implementing this policy, if people are willing to pay for it, we should let them, because that saves the government money where they can put it into a different program. If they aren't willing to pay for it, and if it's an important policy question or important to us that we reduce anemia, then maybe we should be paying for it as a government. Or, so yeah, I think that would be the reason for having two different control groups in that situation.
Thank you.
You're welcome. Okay, and in the chat, Giuliani said that retrospective evaluations are performed after the program is implemented, and prospective evaluations are developed at the same time the program is being built. That is exactly correct. So basically, retrospective evaluation is looking back onto data that already exists. So maybe we're looking back onto some policy from 2005 and the data already exists, but maybe the data isn't perfect. So we don't have all the data we need to conduct a perfect analysis where we have full information of people who are treated and full information of people who aren't treated. And so that makes it more challenging to find a causal effect. Whereas prospective analysis, we typically have data of both the treatment and control groups before and after the treatment period. And that makes it a lot easier to find causal inference without much methodology. So yeah, usually prospective analysis is a lot easier because we have data at the very beginning before anything happens. And so we really need that to estimate a change. Okay. Yeah.
But I mean, with prospective analysis, I mean, after you have the program, you're gonna have even information before the program was implemented. Like, do you know what I'm trying to say?
Yeah, so like if you have like panel data, for instance, you can I know what you're saying. So like,
yeah, so what is exactly the information you can have before
the prospective?
Uh-huh.
Well, you can design it in a way that we're going to talk about causal inference and counterfactuals in the next section, and it will become a lot more clear. But the problem is when we just measure differences between two groups, there might be some sort of bias on our estimates, because maybe there's some difference between the two groups that are affecting our outcome that we can't see. Maybe they're internalized differences, maybe it's ability, maybe it's just motivation or something that we can't see, and that makes it impossible to control for. So even if we do have information on what their income is, what their education level is at each time period, that still might not be enough. Whereas if we have a prospective analysis, we are doing the analysis at the same time the program is being implemented. So we can shape the way that the program is being implemented to ensure that we have causal inference.
Okay, thank you.
Yeah. So like a example would be randomization, would be basically the most important prospective analysis, which we'll talk about later. Prospective evaluations are cleaner, someone asked. Yeah, it is cleaner because it's a lot less work. Usually when we talk about prospective analysis, it means randomization or some sort of way to like randomly assign people to the treatment and control groups. It's cleaner, it's easier, but it's not always practical. So it really depends on the circumstances. There's benefits of both, because if we have prospective analysis, it's this program that's about to happen, and we usually need a larger budget because we're working simultaneously with the project. So it involves a larger degree of investigating and working in conjunction with program implementers. Whereas retrospective evaluations may be harder to find causal inference, but they still are valuable sometimes because maybe we're interested in measuring effect of something that already had happened. So for instance, COVID-19, the crisis we're living in right now, basically maybe we want to know the effect on some different outcomes, maybe labor market outcomes, maybe children's education outcomes. We didn't know this event was coming, so to look back and gather before data might be more challenging. But that doesn't make it a less valuable question, so we will have to find some sort of other techniques, methodologies, which we will talk about more in future classes on how to actually find that causality. And then Nicholas says, you can also gather much more information during the program. So yes, if you are running a prospective analysis, it's easier to choose which data you want and gather it, because you can basically create whatever surveys you want. You can ask whatever questions you want because you have that sample right in front of you. So you can control a lot of the design of the experiment, which gives you a lot more power in terms of what questions you'll be able to answer. Okay. Okay, so, no problem. So this paper is looking at one question, which is the effect of this educational tool, which is flip charts, on how it will affect educational outcomes. And so they're going to use both the prospective and retrospective method and see how the estimates compare, and see if they can find similar estimates using two different strategies. Because really, if they have two different strategies, but they both are causal effects, they should produce similar estimates. However, that's not what they find. Interestingly, although they have the two different methods, their estimates are really different. So retrospective estimates had a much larger estimate than the prospective. And so the retrospective study suggests that flip charts had a large effect on raising test scores and up to 20% of a standard deviation. So they found a really large effect. But then when they conducted prospective analysis, they found no statistical significance. So how can we account for this difference? Why do we run a retrospective analysis and find a large 20% increase in test score outcomes. But then when we run a prospective analysis, we find no effect. How can that be? What do you guys think? Do you guys have any arguments as to why there would be a difference? Anyone? So definitely, you guys will definitely have a better idea why that is after the second chapter. But we can basically put it down to a bias in our estimate for the retrospective analysis. So basically, within retrospective analysis, as we have already learned, we do not have baseline information about our population of interest. This could mean that if we're comparing the difference between test score outcomes between schools, there could be some other differences than the treatment to our outcome. So for instance, we're looking at the effect of this treatment, which is a flip chart. So it's basically this educational chart with different information on math and sciences that classrooms receive to help students' learning outcomes so that they can learn in a different way rather than just a textbook. And the authors are interested in knowing the effect of receiving these flip charts on test score outcomes. So maybe the outcome or the effect for the retrospective study is a lot larger than for the prospective study because there's other factors that are driving the estimate up. So maybe higher performing schools or schools with better principals are more likely to obtain these flip charts, and therefore we're not actually measuring the effect of the flip chart, we're measuring the effect of different factors such as just being a better school or having better students or more money to spend on other input factors, right? So we can't isolate the effect exactly of the flip chart in that case. So yeah, if we cannot isolate this effect of just the treatment that we're interested in, which is the flip chart, we're unable to find a causal estimate, and our estimates will contain an omitted variable bias. So our estimates will be biased and therefore not causal, right? Because we only want that one single chain from our input to our output. But if our treatment input also, if our output is affected by other things besides our input, how can we say precisely what that effect is? Whereas in a prospective study, it's a lot easier because we can say, well, no, randomly we'll say these schools get the flip charts and these schools don't. So if we randomize, which we'll talk about more in chapter 3, then the omitted variable bias will be gone because it was no, there was no choice on the school whether they could obtain a flip chart or not. So then we should not have omitted variable bias. So if you have a better control group for the retrospective analysis, it is more likely that the output is similar to a prospective analysis or not necessarily. Yeah, so basically, if you have a retrospective study and a prospective study that are looking at the same question and they have the similar sample of people, so the samples are comparable, then you would expect to find very similar estimates if you have a good retrospective study, meaning that you can find causal inference with whatever methodology you have. So you can always use prospective analysis as kind of a measure for how your retrospective analysis is doing. For example, if you find prospective analysis really low, the estimate really low, and you calculate an estimate using some retrospective design, and it's a lot larger, you have to go back and ask why is my estimate so much larger? Is my sample size more likely to have a different treatment effect than this group of people? Or is it that there's an admitted variable bias that's biasing my estimate, making it not valid? So those are two things to consider. Maybe your sample responds differently to treatment, or it's that you have omitted variable bias. More likely, it's the omitted variable bias. Okay. Okay, so yeah, that's the problem with bias with retrospective studies. Of course, there's methods to counteract that, which we'll go on about in the next 2 months, I guess. Okay, so what are some examples of something that could bias our retrospective analysis in the situation? For example, if parents who provide better home environments for their children tend to organize more to be able to obtain these flip charts and maybe other school inputs as well. So then if parents in these schools try harder to obtain flip charts and also put more effort into other school inputs, then that's an unobservable bias, which would say that this group is getting treatment, so they're receiving the flip charts, but they're also trying harder in other ways than our control group, so then we would overstate the true effect. Do you guys understand why that effect would be overstated? Or is it unclear? Okay, nothing. So everyone understands perfectly? So unclear. Thank you. Okay, so remember that every unit in our sample, there are many omitted concepts. Yeah, so there's many possibilities for omitted variable bias. But think of this, you're either treated or you're a control. So you either receive the flip chart or you don't. And this is at the school level. So we're looking at comparing outcomes between schools. So if schools who receive the flip charts because they just have parents that care more about their children, and so they'll put in effort for the kids to receive these flip charts. So that makes them more likely to receive the flip charts. But then these parents are also putting more effort into making sure the kids do their homework, making sure they read extra in the nighttime, making sure they receive other school inputs, maybe free lunches, maybe extra classes, tutors. All of these things can confound our estimate and make it appear that the treatment effect is larger than it actually is. Because then we're not just measuring the difference between receiving flip chart and not receiving flip chart. We're measuring the difference between schools who do receive flip charts, who also probably receive a lot more other things better than the control group. So that's how our results become biased. Yeah, thank you. Okay. No problem. Okay, so another possible bias would be if these programs, if the flip charts were strategically given to schools that had worse outcomes. So maybe schools that are more poor that are less likely to afford them, or schools that have worse outcomes to begin with. So maybe I'm administering these flip charts and I say, oh, well, this school, they have a lot lower test scores than the average school. So let's put these test charts or flip charts here and see how it can help. But then if we're comparing the treatment versus control group, they're not equal because this school is actually starting off a lot worse than the other schools that we're comparing it to. So when we measure the effect of the treatment, they're not average, they're not similar to begin with. So then we'll underestimate our result because we'll say, oh, well, the gap is still very small, so maybe it's not an effective program, or that might not be true. It's just that you gave it to a school that doesn't perform well to begin with, compared to other schools who have really high achievers, and so it's not a true result. So therefore, retrospective analysis can either overstate or understate your estimates when you have omitted variable bias. It can go in either direction. So that's why you need to understand your empirical question and what your sample is and what factors you can't observe. So that's where your economics goggles come in, that you need to think critically about whether your estimate is true. Because a lot of the cases, there's no way to test for omitted variable bias. You need to think logically and try and show how it would not be biased, which is normally through a good methodology. And for each methodology, there's a way to test them and to try and kind of show that they're valid. So we'll talk about that more throughout the semester. But just to start off, it's important that you understand what your question is and what things could be affecting your outcome besides your X of interest. Yeah. I'm really paranoid I have coronavirus. I just came to Canada the other day and there were some sick people on the plane, so I'm just hoping that's not me. But yeah, I'm locked away. So, okay. So of course, there can be different directions of bias and severity of bias, so how big the bias is, depending on your data. So that's an empirical question. Okay. So we're going to look at this paper, which compares the retrospective and prospective estimates of the effect of flip charts in Kenyan primary schools. So they're comparing at the school level between schools who receive flip charts and schools who don't receive flip charts. And they actually find that the prospective estimates are a lot smaller than the retrospective estimates. Okay, so that means if the retrospective estimates are above the prospective estimates, which ones should we trust more? What do you guys think? Would you trust? Okay. Prospective. Yeah, everyone agrees. So if we have two estimates between prospective and retrospective, and they're very different, always trust the prospective because it has information about both the treatment and control groups before, and usually there's some sort of methodology to ensure that the treatment is randomly assigned so that there's no differences in unobservable characteristics. So the prospective estimates are always more trustworthy if they're very different from the retrospective. And since the retrospective estimates were a lot larger than the prospective, that means there's an upward bias in our retrospective because it's higher, so then we're overstating the true effect. That's why it's an upward bias, because it's moving your estimate up from what the true effect really is. Okay, so using a straightforward OLS regression, everyone's good with OLS, I'm sure. We're all in our 9th CGLO here. So just running X on Y, basically, using the retrospective data on the test scores. So test scores is the outcome of interest. And so they compare between schools that receive flip charts and schools who don't, right, with no controls. So prospective estimates is giving a wrong effect. No, so retrospective estimates is giving a wrong effect. Okay. So retrospective is the one that we're concerned about because prospective always has the better data. So when we have differences in the two, we trust the prospective. Oh yeah, exactly. So retrospective. Retrospective, we will have to go back and consider why it would be so much higher, and usually we'll be able to find some sort of reason for a bias. Okay, so they find that the retrospective data, the estimates were a lot larger than what the prospective was. Yeah, so that's a great question. So the independent variable would be an indicator variable or a dummy that says the school received a flip chart. So it's just the treatment variable equal to 1 if you receive the flip charts and equals to 0 if you don't. No problem. Okay, so they use different methodologies to try and account for the difference. So the OLS was their main retrospective analysis, and then they do a second retrospective analysis, which is called difference in differences. I'm sure you are all familiar with it, but if not, we're going to talk in great detail about it in a few weeks. So it's a retrospective analysis, because it's using data that already exists and using some sort of methodology to try and get rid of the omitted variable bias by making some assumptions and controlling for something. So we won't get into the details of that, but they use a second type of retrospective estimate, which is methodologically, it's a more strong methodology than OLS because it's using some sort of strategy to eliminate the bias. And it relies on a different set of assumptions, which are more realistic than what the OLS was using. And so even with the diff and diff, they still find a small effect. So instead of the 20% that the OLS found, they still find about a 5% increase in the test score standard deviation for the treatment group. So they find a positive effect still, even though the prospective analysis found no significant effect. So you can see how much closer the diff and diff got to our true effect than to our OLS. So even though it's not perfect, there's some retrospective studies or methodologies that can bring us closer to the true effect. Okay. Okay, so the prospective analysis, as I mentioned before, usually involves a randomization. We're going to talk about randomization more next week, I promise. It's a very basic concept, but basically you're randomly assigning a group to treatment and a group to control. So we're saying, okay, we have 100 schools, 50 of them will receive the flip charts and 50 won't. And that's randomly. So if we randomly put them in the two groups, the average difference between different characteristics such as quality of principal, parent motivation, kids' test scores, all of these things should be equal across the two groups to begin with. Then from there, it will be a more accurate measure of the effect when one group receives the treatment and the other doesn't. Sorry. Okay. Okay, so yeah. They obtain much different estimates in the prospective analysis and then from the other to retrospective analysis. So they basically found identical results in test score outcomes between the treatment and control group, suggesting that the flip charts don't actually improve test score outcomes. So that's an interesting result because there's many reasons to think that flip charts could help. Oh no. I'm gonna die. Okay. I'm sorry. Okay, so basically, since we know that our prospective analysis is always preferable to our retrospective, I started writing it as retrogressive. That's wrong. Ignore that. That's just me making spelling errors. Okay, so then we should trust the results from our randomization, which is our prospective study, against our other two retrospective analysis, such as the diff and diff and the OLS. Does that make sense? Why? I think it does. So, okay, so then just some background about the actual paper. They looked at the Kenyan children or schools that received the flip charts, and basically half of the children in rural areas reach grade 8, which is the final grade of primary school in Kenya. So less than half in rural areas reach that level. And then entrance into secondary school. So secondary would be like grade 9 to 12 maybe, is based on some exam. So it's the certificate of primary education, which is taking at the end of grade 8. And so they look at 2 neighborhoods in Kenya that have both below average income, so they're comparable in income. And the flip charts and other visual aids are really rare in these schools. So they find that less than a third to begin with have access to any flip charts. Oh yeah, so in the previous slide, can we say that unfortunately the effect of the program was not very relevant? Yeah, we can say that there was no significant effect of flip charts, and so we couldn't recommend as a policy that government should spend money implementing more of them because it doesn't seem that effective to whatever the control group was using for educational supplementation. Okay. So yeah, less than 1/3 of these schools had any flip charts. Even textbooks in these schools are rare. So about 40% of students in grade 8 even had a textbook in math and English. And then less than 15% had textbooks in sciences or other subjects. So textbook use is rare, flip charts are rare. So they wanted to know the effect of providing this visual information using flip charts. And so these flip charts included 2 sets of science charts covering agriculture, general science, and then a guide for math, as well as the geography guide, so map. And then they all contain like different charts bound together. And so they're sharing the charts across the school by bringing into classrooms when the class intends on using them. But mainly the charts went to grades 7 and 8, which are the grade 8, take the test. So that's what we're going to be looking between. And it's interesting because authors think that there's reasons that these flip charts could improve learning outcomes. So they say that almost all students recall seeing a picture more often than having read a word or sentence. So images are maybe a better learning material if it helps you remember better. Also, there's variation in how students learn. So maybe I'm better at learning things by reading, but maybe some of you guys can understand something better with a visual aid. Maybe you need to see a graph to understand. So having that extra visual material might help some students that don't normally have access to that. And then also, textbooks are very expensive, so maybe flip charts can be a cheaper alternative in some situations. Also, flip charts are visual, so you don't need to know English very strongly to understand it, which students in Kenya in this rural area have limited ability in English, so this can help them learn better maybe. So this is an example of the flip chart they were given. You can see very visual. It shows some math divisions, pie charts to show fractions, weights, time, percentages, all that stuff. So yeah. Okay, so basically they're using the difference in these practice tests. Okay, that's my dog. So they're taking this test that is very structured, so it's not given at the school level, it's given at a district level, ensuring that the test is very similar across schools, which is important because if one school writes an easier test than the other school, then that's the measure, that's the effect we're picking up. We're not picking up an effect of the flip charts, we're picking up an effect that, oh, this school just writes easier tests. So that is also a problem. So you need to make sure that your outcome is similar across schools. So we know that the test scores will be a consistent measure because it should be very standardized at each school. Were the tests applied specifically to evaluate the policy? No, the tests are what the students need in grade 8 to get into the next level of school. So in grade 8, they're still in primary school, and to get into secondary school, they need to take this test. It's basically an entrance exam. So it already existed before, yeah. So yeah, we don't want the test to be more hard across schools or also over time. So that would be things that would bias the charts. Especially, this is, for example, in the retrospective study, if we're using multiple years in our sample and just saying, oh, well, these schools received treatments and these schools didn't, and you're comparing over a long panel of time, that would especially bias your results if the difficulty of the test changed over time, because you really can't know that. And so you won't be able to control for it. Okay. Also, each test contains 7 topics. 4 of those topics were covered by the flip charts. So you know that if these students perform well in these subjects, it has something to do with the flip chart. So if we're giving students a flip chart on sciences and their test is only on reading, then of course there won't be effect. So that's why you need to be careful about your study design and that your input is actually affecting an output that you care about. Okay. So yeah, as we said, the retrospective design was an OLS and a diff and diff, which isn't really important in methodology for the diff and diff. You should know OLS. And then the prospective was a randomization. We talked about why the retrospective analysis may be produce biased estimates based on different qualities of the school that we can't control for in our data because we can't see them. So yeah, basically retrospective analysis will be biased if it cannot address the issue of unobservable inputs. So motivation, ability, how much do your parents care about your outcome, stuff like that. All right, so that would bias our estimates. So yeah, just this is talking about the data for the retrospective analysis. I don't think it's very important, so we'll skip it for now. Oh no, I'm so scared. Okay, so this is showing the next table will show us the results of our retrospective analysis, and both the OLS and difference in differences. And so we'll look at that now. All the regressions include subject and grade fixed effects, and control whether the school was in a group that received textbooks or grants through another program. So this is an attempt to control factors that also affect our outputs. So by including subject fixed effects, basically you're only comparing between grades within a given subject. So we only want to compare scores in a math test between other scores in a math test. We don't want to compare scores in a math test versus a reading test because they aren't comparable, right? So we only want to compare within one group. And then grade fixed effects is the year of study. So we only want to compare between students in their 8th year to students in their 8th year, and students in their 7th year to students in their 7th year, which should be obvious because maybe tests in the 8th year are harder than tests in the 7th year, and so that would be an invalid comparison as well. But you can see that all of these things that they're controlling are observable. They're not unobservable. So if there's differences in our unobservable characteristics, there's going to be a bias. Okay, so this is the table. Table 1, you can see retrospective estimates of effect of the 4 flip charts in grades 6 to 8. And so they're normalizing the test scores to 1 year. And you can see, so there's 1, 2, 3, and 4 are the OLS specifications. And then 5 and 6 are the diff and diff specifications. And so it said column 1 to 4 is the different subjects. So doesn't say exactly what the subjects are, but just know that these 4 are 4 different subjects. And you can see, so this is the estimate we care about, the number of charts in the school. So you can see a positive effect all the way across. They show you the significant star. So when you see 3 stars, it's significant at the 1% level, right? Here it's significant at the 1, or for 1 star, and that's at the 10% level. So the more stars, the more statistically significant it is, right? So all across the board, except for one subject, we see a strong statistical significance and also effect between about for the OLS, for these 3 estimates, the first 3 columns, like 19 to 20% increase in your test score compared to the control group, right? Does that make sense? So 0.192, you would say the treatment group sees, or if you receive a flip chart, or so basically for an extra flip chart in the school, the grades will increase by 19.2%. And that's statistically significant at the 1% level. You can see here the effect ranges between 19 to 20%, except for this one subject. I can't remember what it is. It's only significant at the 7%, or it's only significant at the 10% level, and shows us an effect size of 7%. Right? Any questions on how I interpreted those estimates, or is it very clear? Very clear, great. And then for the diff and diff strategy, remember it's a different methodology that uses stronger assumptions, which we'll talk about later. And so it can tackle or can address the omitted variable bias in a better way than the OLS can. So you can see lower estimates. So it only estimates an effect of about 15%. And then charts times flip charts. Oops. Yeah, what's your question regarding the coefficient? Sorry. it's 19.2 extra grades for each chart. Okay, so for each chart. No, so basically we just have a chart, a flip chart, and it contains multiple subjects. And then we're looking at the effect for different subjects. So row 1 is one subject, say it's math. Row 2 is science, maybe, I can't remember. Row 3 is reading, and row 4 is geography. So even though the charts contain all the subjects, in each column, we're only looking at one subject. So then the effect's only telling us the increase in a test score regarding one subject. Is that clear? Okay, great. So yeah, the diff and diff strategy is a stronger prospective analysis than OLS, and so it was able to reduce some of the bias in the estimates. And yeah, but it's still not the same as what our prospective study is. Can I repeat the answer of the last question, of the coefficient question? Yes, I can. So I said that each chart contains all of the subjects. So maybe there's some math, maybe there's some science, geography. They're all combined together, all of the subjects. And so we're looking at the effect of how many charts they have in a school on test score outcomes. So all of the subjects are captured in the graphs or the charts. But when we're looking at the estimates in this table, each specification, so column 1, 2, 3, and 4, they all represent different subjects. So when we measure the effect of having a chart on our test score, we're only looking at the test score of the subject. Say it's mathematics. So having a chart of all the subjects in a classroom, the more charts we have, so if we have one extra chart in our classroom, it will increase the school's average test score of mathematics by 19.2%. That's how you would interpret it. Is that clear? Okay, no problem. Okay. And then these are just other controls they added to the specifications. So they controlled for things like indoor classrooms. So maybe students learn better if they're in an indoor place than an outdoor place. This is a really rural area they're looking at. So kids who study outside, maybe it's just harder to learn. There's more distractions. They don't have tables to write on, so they'll want to control for that. It's also a control for income in a way, because students are learning in an indoor classroom. Obviously, the school has more wealth than an outdoor classroom. So that's a kind of control for income. Roof does not leak, another proxy for quality of school or income of school. Blackboard, so does the classroom have a blackboard, which can also affect learning quality. Textbooks per pupil, so for each student, how many textbooks do they have? That will obviously affect test score outcomes, because maybe students use this textbook to learn, so the more textbooks they have, the better they'll do. That's something you want to control for. Again, desks, how qualified the teacher is, how much they're trained. More trained teachers will probably teach their children or students better and will get better test scores. So these are observable things that they want to control for, right? But they're all observable. So maybe it's not enough sometimes. Okay. That's what I said. So yeah. Basically, since the schools without the flip charts had textbooks, the retrospective results imply that flip charts are more cost effective compared to textbooks, because they're much less expensive and then the authors find a positive effect of these flip charts on test score outcomes. So then their policy recommendation would be to replace textbooks with flip charts. But using our prospective analysis, we see that that's not true, and they're just capturing some sort of difference between the two types of schools. So yeah, that is really important when you're considering the final goal, is to make a policy recommendation. If your results are biased, then you're not able to make an informed decision. Okay, so this is the results of the prospective estimates, and you can see basically past perfect. Okay, so look at this flip chart school column, and it has the coefficient and standard error. So it looks kind of different than the other table, but the other table just had the standard errors below the coefficient. This has them next to each other. So to find the statistical significance, right, we're dividing the coefficient by the standard error, and that gives us our t-value. And if it's greater than 1.96, for example, it would be significant at the 1.5%. But you can see nothing here is significant. So clearly, regardless of what subject, the treatment group doesn't see a significant increase in their test score outcomes compared to the control group. So much different results. Okay. Any questions? No? Okay, so let's take a 10-minute break. I'll see you guys at 6:07, 6:08. Okay. Oh wait, no, you're guys 7:08. Sorry, I'm an hour behind now. Okay, goodbye. Okay, we're gonna start again. Oh. Oh. Sorry. Okay, we're gonna start again on chapter 2. Any questions before we get going? There's a couple questions in the comments, or just one, by Santiago. He said that I interpreted the coefficients wrong as percentage increases, which is true. It should be changes in standard deviation because it's a normalized test score. So you can think of it as differences in standard deviations. So yeah, thanks for correcting me. Okay, I'm gonna share my screen. Where are we? Oh. Okay, so chapter 2 is about causal inference and the counterfactual. So we talked a lot of we did a basic introduction of impact evaluations, and we started talking about why it's important to find causality as a policy question. Now we're going to actually consider what causal inference is. Okay, so I'll say this now and I'll say it again. What makes economists different, and in my opinion much better than statisticians, is that we don't just look at correlations or look at data as a whole. We take our data and we strive to understand it in a way at which we look at causal relationships, which is really important for policy, for research in general. So yeah, that's our main goal as economists, really, is finding that causal inference, at least as empiricists. Obviously, theoretical economists are doing other nerdy things, which I do not do, but this is my opinion. Okay, so although cause and effect questions are really common, answering them accurately is actually really a challenge, as you'll come to find out, especially during your thesis this year or next year. It can be really challenging to come up with, or to answer the question. You might have a million in your head, but the steps to finding the answer are going to be incredibly challenging. So how can we isolate the effect of X on Y in a really messy world where everything's changing, right? This isn't a science like chemistry where we can take a tube and look at how two things react with each other. We have to work in a world where people are making many different decisions. There's different actors, there's different shocks and economy changes that are all happening at once. So how do we isolate for one effect of interest? So impact evaluations are how we do this, how we were trying to answer cause and effect questions. And of course, as you guys know, just because two variables are correlated does not mean they're causal. Are we done? Okay. Yeah, Giuliani asked if the other slides of the first chapter, are we done? Those aren't supposed to be in there. I wasn't going to teach that paper this semester. It's from last chapter or last semester. So just ignore it. I'll delete the chapter and upload them without those slides. You don't need to look through them. Okay. So as I was saying, correlation does not equal causation. That's why we can't always just run an OLS regression of what is the effect of X on Y and expect to obtain a causal result, because maybe we're measuring the effect of X on Y, but we also have 20 other things that are affecting Y that we're not getting rid of. So we're not accurately measuring the effect. So consider the following example. Suppose people who go to the hospital on average have worse health outcomes than people who do not go to the hospital. So people who go to the hospital are more sick than people who do not go to the hospital. Does that mean that going to the hospital makes people sick? Does going to the hospital cause you to get sick? What do you guys think? I mean, the answer should be obvious, hopefully. Right now, if you go to the hospital, it's going to make you sick, but in normal circumstances, looks like a fake news article. Yeah, double causality. Yeah, so you guys are saying something else is going on besides the just one-way causality of going to the hospital and health. So it could also be that health is affecting you going to the hospital. So it's not that going to the hospital makes you sick, it's that sick people go to the hospital. So yeah, that's what, what's your name? Sorry. Nicholas said. Double causality or reverse causality. There's some sort of relationship going both ways. And it's probably more likely that being sick makes you go to the hospital more than going to the hospital makes you sicker. Okay, so yeah, hopefully that question was obvious. And so what we call that is selection bias. Okay, because sicker people are selecting to go to the hospital more than healthy people, right? That's selection bias. There's sorting into hospital treatment, and that sorting is determined by your health. Is that clear? Or no? Yes. Okay. Yes. 2 yeses. Unanimous. Everyone understands. Okay, so look at this table. We have groups. We have 2 groups. People who go to the hospital and people who do not go to the hospital. And now let's compare their mean health status. Okay, well, first you can see that obviously more people don't go to the hospital than do go to the hospital, so there's a large sample size in the second group. And then take their mean health status. So in this case, health status is ranked from 1 to 5, with 1 being perfect health and 5 being the least healthy. Okay? So we can see that between the 2 groups, the no hospital group is healthier than the hospital group because their health status is 2.07, which is better health than 2.79, right? So people who don't go to the hospital are healthier than people who do go to the hospital. If we were to just run a simple OLS regression, where Y is our health status and X is our going to the hospitals. I actually want to see if I can make it. Wait, new share. I'm gonna try something. If it's awful, I'm never doing it again. And no one remind me of this moment. Okay. Oh. So for individual I, that's a Y, right? Fun to stay at the YMCA. That's a Y. I made it worse. Equals alpha. Man, this is so awful. What's my treatment status? Let's call it an X for now. And then, of course, plus our standard errors. Oh, there she goes. Okay, so YI is our what? Our health outcome, our health status. You guys can see this, right? Yes. I don't even know how to spell right. This is why I don't write. Yeah, okay. Health status. Okay, alpha is our, what's alpha? Intercept, yeah, it's our intercept or our constant term. Oh my God, this is so hard. Okay, so xi is a dummy variable. Equals to 1 if hospital, if you go to the hospital. And then this is our error right here, error term. Okay, and so this is the coefficient of interest, right? This is what we want to estimate. So if we were to run this regression and we want to know the effect of going to the hospital on our health using the data we just saw in that table, remember that the group that goes to the hospital is sicker than the group that doesn't go to the hospital. So then we'll find a negative coefficient of going to the hospital on your health status. Right? Does that make sense? Why we would get a negative coefficient if we ran an OLS regression. Because the hospital group had lower health than the non-hospital group to begin with. And that's not even a function of going to the hospital, that's just because sicker people tend to go. But then we will wrongly estimate a negative fact, and then consider if we have policy evaluations after, and we're telling the government, don't invest any more money in hospitals, they are not good for health, they just make people sicker. We should get rid of all the hospitals. That would be awful advice, right? So these are things to consider, what your selection bias is between your treatment and control groups. So that's basically differences in baseline outcomes. Is that clear? Okay, I'm gonna delete this awful drawing. No one needs to save that, right? If you want me to save it, say yes now. If not, I'm gonna delete it. Oh, no, what did they say? Oh, there are no lies. Okay, I'm not gonna save it. Oh, what happened? Ah, okay, back to our notes. So yeah, we can see why an OLS regression would produce negative estimates, which isn't reflective of the true causal effect. Okay, so, for example, this is a common setup that we're going to use. So I'm just going to define yi as our outcome variable for individual I, and then let di denote treatment status. So that's what our x was before, but it's fine. You guys can follow along, I'm sure. So di equals 1 if individual I went to the hospital, and equals to 0 if they do not go to the hospital and they receive no treatment. Okay, then from there you have two potential outcomes. Either you can have potential outcome 1 if you go to the hospital. So potential outcome 1 is y subscript 1i if you go to the hospital. So if di equals 1. And then your other possible outcome is y0i, which is you don't receive treatment. So di equals 0. And for individual I, we would like to know the difference between y1i and y0i, which can be said to be the causal effect of going to the hospital for individual I, right? So we want to know the difference in health between going to the hospital and not going to the hospital for individual I. I'm saying individual I because when we are looking at one individual, we can control for the fact that it's the same person. So there's no selection bias, right? There's no differences in choosing to go to the hospital or not between groups because it's the same person. Okay, so in that case, the causal effect is just the outcome of going to the hospital minus the outcome of not going to the hospital. So y1i minus y0i. And that's just for, that's only causally, that only has inference for individual I. So it's not an average of treatment effect, it's just the treatment effect for individual I. Is that clear? Or no? Awesome. You guys are so smart. Okay. Can I repeat, please? Yes, I can repeat that. Okay. So like I was saying, you have two potential outcomes. The outcome you observe if you receive treatment. So if DI equals 1, you will have potential outcome Y1I from receiving treatment. You will have a different potential outcome, Y0I, if you don't receive treatment. So you have two potential outcomes. You can either get treatment or you don't get treatment for one individual. I can go to the hospital or I don't go to the hospital. And then for that individual, the causal effect of going to the hospital on my health outcome is Y1I minus Y0I. But that's just the effect for me personally. Okay, so it's not like an average treatment effect. I can't say if this is my treatment effect, it's true for the whole population. So this isn't giving us any information on policy because it's only true for me. Just for an example. No problem. Okay. So, like I said, it's not necessarily good for policy advice because different people will have different treatment effects. Maybe some people respond really well to hospital treatment, whereas other people, that doesn't matter. They're just stay low health always because they have a lot of severe conditions and going to the hospital doesn't help their actual health status that much. Whereas if I break my arm, I go to the hospital, they put it in a cast, and then I'm better. So it really depends on the person. So there will be different treatment effects. Okay. The biggest problem we have about causal inference is remember how we compared between the two potential outcomes, our Y1I and our Y0I. The problem is that we can't actually measure this because we can never observe both potential outcomes for one person in the same moment of time. So I cannot choose to go to the hospital and not go to the hospital. So I can't know the difference in those two outcomes. Right? That's logical. That's why they're potential, because I can only do one or the other. I can't do both. So I can't actually compare the outcomes for one individual. Something we will never know. Exactly. The biggest mystery of economics. But there's approaches to get around it, of course. So that's why we look at differences in average outcomes. So we then compare the differences in average outcomes, in this case health, for individuals who do receive treatment against individuals who do not receive treatment, right? So we have a whole population and we're looking at within that population, some of you guys go to the hospital, some of you don't. Then we can compare what is the effect of going to the hospital on health. Okay. But then when we do compare groups, so before when I was comparing myself to myself, there's no selection bias because I have the same characteristics, I'm identical to myself, everything is controlled for, unobservable. I have it's just, yeah, I think that's logical, you understand, right? When it's between one person, all of my qualities are the same in each moment. So there's no selection bias. But when you compare between two groups, there's this problem of selection bias because then sicker people are choosing to go to the hospital more than healthy people. So then when we run a regression of going to the hospital on health outcomes, we're going to create this bias that's not going to give us an accurate estimate. So if you guys look at this equation, this is in terms of expectations. So basically on the left-hand side here, we find our outcome of interest is the expectation that of our yi, so our health status, given di equals 1. So given we receive treatment, minus the expectation of yi given di equals 0. So our health status if we don't receive treatment. So that's our observed difference in average health. That's what we observe. That's what we observe when we run an OLS regression of going to the hospital on health. The difference between health for people who go to the hospital or who don't, who go versus who don't go. You guys understand the left-hand side? Or no? Any questions on that? It's just in terms of the expectation. So here would be the average difference between the two groups. Okay, so then on the right-hand side, we're going to have two different terms. So what we want to estimate and what's going to be attached to our estimate, which is the selection bias. So what we want to estimate is for the treatment group, basically. So for me, individual I, for example, the difference of basically your health status, Y1I. So if you were to go to the hospital versus your health status if you were not to go to the hospital, Y0I. But they both say, notice, di equals 1 because we want to compare within the group that receives treatment. So when we look within one group, we don't have selection bias because we're controlling for those individual characteristics. That's why we like controlling or comparing within one group, right? So we have that effect that we're really after, that we want. And then unfortunately, we have this other term called selection bias, which is not good for our estimate. It will not reflect our true effective interest. And that's just the difference between health status between the two groups. So before you even go to the hospital or before treatment is administered, you can see it's our baseline health. So the expectation of Y0I given DI equals 1. So Y0I, remember, is like the health status of not going to the hospital for the group that goes to the hospital. And then the health status of the group that does not go to the hospital before they go to the hospital. So it's really comparing the health of the group that goes to the hospital versus does not go to the hospital, but before anyone goes to the hospital. So if there's any difference between these two terms, the averages of the two groups, that's bias because then they're not comparable. Then one group was healthier than the other to begin with, and that's going to bias our estimate upwards or downwards. Right? So in this case, our selection bias term, the group that goes to the hospital will be lower than the group that does not go to the hospital. So if the group that does, the health of the group that does go to the hospital is lower than the health of the group that does not go to the hospital, we'll get lower minus a bias. Is that clear or no? Basically, we have our observed health outcomes is a function of the treatment effect that we want, the treatment effect of the treated, plus a selection bias term, which shows us the difference between health status between the two groups before either group receives treatment. So that's why it's the Y0I That's the doesn't receive hospital group or potential outcome. So you have two groups, DI equals 1 and DI equals 0. So goes to the hospital, DI equals 1, does not go to the hospital, DI equals 0. Then you have two potential outcomes, which both groups should observe. So the group when they go to the hospital and when they don't go to the hospital. So we should have both those potential outcomes for each group. I mean, in reality, we don't, but when there's a difference between the Y0I potential outcome between the two groups, then our results will be biased because that's captured in our estimate. The idea is that only the effect is observed. No, the idea is that the effect we observe is going to be a function of our treatment effect that we're interested in, and also a selection bias term. So what we observe, it might not be the true effect when there's differences in Y0Is between the two groups. I would recommend you guys just to write out this equation more times, because when you write it out, it does make a lot more sense. Because you can break up the EYYI on the left-hand side to the Y1I plus Y0I for both groups, and then you can distribute them as this. So if you write this out and expand it and then sort it into these two functions, it will be a lot more clear how there's two potential outcomes and two groups. Okay. Okay, as I already said, the first term on the right side of the equation is the causal treatment effect that we're interested in, and it gives us the average difference in health outcomes for individuals who receive the treatment. So it's not really after, before, I guess, but it's if they receive the health treatment versus if they don't receive the health treatment. So actually saying after minus before is wrong because we don't observe both, but suppose we can see both of the potential outcomes, that would be the causal interest. And then that term above is called the average causal treatment effect of the treatment on those who are treated, because we're only comparing between the group who receives treatment, DI equals 1. And that's important because then we can control for selection bias. When the people if we're comparing between one group, they have the same characteristics, so there's no bias. So yeah, as you can see, I just wrote this term. So the expectation of Y1I given DI equals 1 minus the expectation of Y0I given DI equals 1 is just the expectation of Y1I minus Y0I given DI equals 1. You can see they have the same condition or group, so you can combine them. And yeah, that gives us the effect of, you can see for a group that receives the hospital care, the health outcome if they receive the hospital care minus the health outcome if they don't receive the hospital care, right? That's the Y1I minus the Y0I. Is that clear or no? Okay, well, think about it. Come back to me if there's any questions, of course. And so the goal is that we only want this treatment effect. So we want to eliminate the selection bias term because we know that people who go to the hospital are more likely to have worse health than people that don't go to the hospital. Put that in other words, people who do go to the hospital have lower Y0 eyes. So their potential outcome of not going to the hospital is already lower to begin with. So that just means it's a sicker population. Okay. Okay, I think we're gonna start topic 2 on Wednesday. And also on Wednesday, we will be going over some coding. It will be pretty basic, but if you have any concerns about the assignment that's going to be due on April 26th, definitely I recommend coming to the class just so that you feel comfortable answering any questions. All right, any questions on what we just covered right now with selection bias? I want you guys, if you have free time, to try writing out the selection bias equation. Make sure you can be able to break apart the difference between the treatment effect and the difference in the potential outcome Y0I for the two groups. All right. So yeah, I'll be posting assignment 1 before or on Friday, and it will be due April 26th at midnight. That information is also on the calendar I posted in SIGA, in case you forget. If there are no more questions, I will end it. Feel free to. No more questions? All right. Well, I'll talk to you guys on Wednesday then. And I will end the meeting. Okay. Goodbye. You can always email me too if you have any questions about class and didn't want to ask now. Okay. Have a good night, everyone.